Want to do a test?
Okay, can you hear me?
Hello? Yeah, okay.
Great.
Okay, so we're finally set up there. We arrived 15 minutes early. Yes. Okay, so this is Michael Wagman from Fermilab. He won the Kenneth G. Wilson Award recently. He's been an associate scientist at Fermilab since 2019. Before that, he was a is it Papadaro?
Florida.
Yeah, Massachusetts, MIT, Massachusetts Institute of Technology. Previous to that, he earned a PhD at the University of Washington in Seattle, and he's a member of the NLPCD collaboration. And he also makes a very nice website. I think a lot of the students should take a look at his website and try to emulate that. It's a great way to advertise what you're doing. So today he's going to talk about big question I've always had in my life is why do the nuclei stick together? Because it seems like a simple question, but it's really the answer requires a bit of theory and math, and here's Michael will explain it to us all.
Well, thanks very much, Terrence, for the kind introduction. Thanks, everyone, for the invitation to come out here. I've had a really good time for the last day and a half, and looking forward to talking with you all some more. And now that we've achieved the first task in computational physics of get logged into the right computer, let's go for it. Okay, so this is a talk about the Standard Model, which we all know the four forces involved: gravity keeping us on the floor, electromagnetism stopping us from going through the floor. This talk is mostly going to be about the strong nuclear force, which is described in the Standard Model in terms of the quarks that are inside of protons and neutrons, which I'll collectively call nucleons, that exchange gluons in much the same way that we think of electrons exchanging photons being the underlying microscopic picture of quantum electrodynamics. And the other force that I'd like to highlight here is the weak force, which is responsible for many radioactive decays of nuclei and of free neutrons, and is also where the neutrinos that we see or try to see come from. And so I want to take a brief detour into neutrino physics before we dig in more to the strong force. They're intimately connected in that neutrinos come from nuclear processes. So the sun is a great neutrino lamp. It's producing millions of neutrinos that are streaming through you every second. Many of you know much more about this than I do and are actually trying to build satellites to go up and collect all of the neutrinos near the sun, which I am phenomenally impressed with as a theorist. But we have a great model of where these come from, theoretically, as the byproducts of the fusion reactions taking place in the sun. And we've learned a lot from these. In particular, in experiments dating back more than half a century now, we've been trying to use the neutrinos that we measure on Earth to test things about our understanding of the sun as a nuclear reactor. And some of the initial tests came out differently than expected, in that we detected neutrinos coming from the sun, but the pioneering experiments in the Homestake mine in the 1960s detected them at a less than half the rate predicted by nuclear theory. Tremendously hard experiments filtering out atoms a day from tons of cleaning fluid, and there was a lot of worries that there could just be hard systematics involved in these. However, with half a century of more data, we now understand that there was just something more subtle going on, where the electron-flavored neutrinos produced at the sun have been spontaneously oscillating mid-flight and show up as a roughly equal admixture of these three different flavors by the time they get to Earth, which is weird because that kind of mismatch between the flavor basis and the propagation or mass basis can only happen if neutrinos have mass, but in the Standard Model, they're not supposed to. So we have some beyond the Standard Model physics that we're really manipulating here in a lab when we look at neutrino oscillations. And there's a lot that we still don't understand about it. So in particular, we don't know the ordering of the neutrino masses. We're only able to measure these two mass gaps from oscillations, and it's not clear whether the large gap is between the heaviest of them or the lightest of them. There's also two different types of masses allowed, depending on whether neutrinos are really their own antiparticle or whether those are separate particles that can never mix with one another. And there's a new generation of neutrino experiments that are trying to shed light on some of these questions. And this is something that Fermilab is intimately involved in with the ongoing construction of the deep underground neutrino experiment that's going to produce the world's most intense beam of neutrinos at Fermilab, send them through 1,300 kilometers of rock, and then collect them in the same homestake mine, well, an expanded version of it, in South Dakota. And, well, sorry, close by the original homestake mine. And these sort of experiments will be able to shed light on questions about whether neutrinos and antineutrinos oscillate differently, hopefully pin down the mass ordering conclusively, probe whether there could be other sterile neutrinos that we're not familiar with, and give some hints on whether neutrinos and antineutrinos might even be able to oscillate into one another. Other neutrino experiments are poised to go after that question in particular, with the ongoing generation of neutrinoless double beta decay experiments that are trying to directly test for this difference between Majorana and Dirac masses of the neutrino. And this is about where the quarks start to enter our story of neutrinos. As what will be measured in a double beta decay experiment is the half-life of some nucleus that you only expect to decay through this specific channel with kinematics you can isolate if the neutrino and antineutrino can annihilate with one another. And so you'll get out some number for the lifetime. What you'd like to know is the mass of the neutrino in absolute terms that was responsible for that decay. And that's a theory relation between those two of the QCD matrix element that relates your measured half-life of this decay in this nucleus with the fundamental parameter of the neutrino mass involved. Similarly, at Dune, we're going to get exquisitely detailed pictures of the outgoing final states of neutrino nucleus collisions inside of liquid argon time projection chambers, but inferring the incident neutrino energy distribution that created those is a hard problem that requires insight from nuclear theory. And if we want to really be able to say we found new physics beyond the standard model in these sort of experiments, then we better have our theory rigorously grounded in the standard model. And that means we need to somehow get from the theory of QCD to the phenomenology of nuclei involved in these experiments. And at the level of precision that the next generation of neutrino experiments is going to need, we're going to need to do a more sophisticated job of this than previous generations of nuclear model building. Okay, so lattice QCD, that's weird. There's a text block missing there, but we'll hope there's not too many of those. Can hopefully help in this by giving us a way to microscopically simulate the interactions of protons and neutrons with neutrinos or other probes directly from the level of QCD. And yeah, there's an equation missing here. Okay, it's just this slide. It's fine with... No, we don't really need equations. The point is just that you can simulate things like the response of a proton to a background electric field that you apply. And that you can translate into these things called electric and magnetic form factors that just parameterize the low energy response of a proton to an applied electric or magnetic field. These are things that we have measured to death a long time ago. And so it's validation for lattice QCD that the matrix elements that are predicted from these sort of simulations collapse on top of the phenomenological curve for what these form factors should look like. And all that's going on in these bottom plots with all the letters and numbers is that there's a bunch of just raw data from lattice simulations at different pixelations without even the full continuum limit taken. And it all basically just collapses on top of this curve. So there's nothing too sophisticated that needs to be done to get this kind of agreement here. It just works out of the box. There's an analogous set of form factors for describing the response to a weak interaction like a neutrino probe. And here there's more complications in the lattice calculations just because those axial currents couple really effectively to pions, which are light particles copiously around in these kind of simulations. And so there's been a long recent history of groups trying to pin down all of the systematics in these calculations. And we're starting to see a nice convergence where multiple collaborations have performed calculations using physical quark masses, dealing with all of the uncertainties you'd like to deal with, and get those three upper bands that all kind of collapse on top of each other for this important axial form factor. On the other hand, the blue band was the state-of-the-art phenomenological expectation for what it should be based off analyses of old deuterium bubble chamber data. And there's a 1 to 3 sigma discrepancy between the two of them, depending on what energies you look at. And on the lattice side, folks are working hard to try and test the remaining systematics and leave no stone unturned. But there's starting to be good enough agreement that it's also well motivated to worry about the systematics that arise in going from old handscan bubble chambers of deuterium to nucleon form factors where you have to back out some theoretical nuclear correction with some model of deuterium. And the group by Aaron Meyer and collaborators that most recently did a thorough analysis really worried about all of these things and tried to put in the best uncertainties that they could, but there are issues there that have not been fully understood. And we could be looking at the start of lattice QCD, teaching us things that we need to know for these neutrino experiments that we'd have otherwise had the wrong expectations for. Okay. Sad. How hard would it be to connect this projector to my laptop? Nah, it'll be fine. It'll be fine. We don't deeply need slides. Yeah, no, this just was supposed to have a couple of points about what's easy for lattice QCD and what's hard for lattice QCD. And the big takeaway is that it's complementary sets of things to what's easy and hard for experiments. So it's easy for us to change between an electric background field and a neutrino background field in a way that's very hard to do experimentally. It's easy for us to disentangle different spins and flavors of the quarks in a way that, again, is hard to do with polarized beams. On the other hand, it's very hard for us to simulate real-time dynamics. It's very hard for us to simulate large nuclei. And those are really the most important ones, but that's kind of challenging when you're ultimately trying to simulate neutrino-nucleus interactions. So the other perspective on why I think that lattice QCD has something to offer theoretically is just that we don't understand much about strongly coupled field theories as field theories, and there could be more out there than meets the eye. We know that the visible matter that we see is mostly dominated by energy from QCD. Your mass is 99% gluon energy. Everything else is a rounding error. The strong interactions are a really effective way to store energy. It's where most of the proton mass comes from. And so it's natural to ask whether the other dark matter that we measure out in the universe might have some origin in a strongly coupled dark sector. And if you want to try and understand these kind of questions, people have done phenomenological studies for the last decade or so that have shown that you can get viable theories of strongly coupled dark matter with your constituents ranging over huge ranges of scales. And some of the best bounds on what this should look like come from things like bullet cluster observations where dark matter halos go right through each other that tell us that they can't be too strongly interacting. But the bounds really come out at sort of the same level as the strong interactions that we know from QCD. So it's very much still on the table that you could have a QCD-like dark sector. But if you do, the exact phenomenology of it will depend very intricately on whether and by how much the dark nuclei bind. So for these sort of philosophical reasons and technical reasons that lattice QCD simulations are just much more expensive when you go to lighter quark masses than heavier quark masses, we've started to explore the whole range of scales that quarks could come in, down from the up and down quarks that make up protons and neutrons that are much, much lighter than the other scales in QCD, to the bottom and top quark that are much heavier. Yeah, and so the question that I'm going to sort of walk through here is trying to understand perhaps the most basic property of nuclear physics, depending on the quark masses, which is just whether the interactions become stronger or weaker as you raise the quark masses, and whether the binding energies of nuclei go up or down. And you can convince yourself that it should be either way. If you have some model of a nucleus as like a gluonic molecule, where like protons and neutrons are like an atom held together by these gluon exchanges, then the binding energy of your molecule should go up as the masses of the constituents go up. On the other hand, if your binding energy is coming from protons exchanging pions, then the strength of pion exchange gets stronger as your quark masses go up. So the only one that is worth writing on the board here is sort of that in a model of pion exchange, as your quark masses go up, your binding goes down. If you have a picture of a gluon molecule, then as your quark masses go up, your binding should also go up. And so getting some qualitative handle on what our cartoon picture of a nucleus should be kind of comes along for the ride with being able to just predict this quark mass dependence and whether the nuclear forces should get stronger or weaker. We know a little bit about this from effective theories that are able to describe light quarks. However, not as much as we'd like, because it ends up being very sensitive to lots of details of the effective theory that we don't have well constrained from data. And depending on your assumptions about these, you can kind of get any answer you want. For medium quark masses, okay, I'm going to try and switch over here. Wait, no, this is just a problem with Adobe. I've seen this before. Let's just do this and figure out some way to full screen this. Have it there. Yeah, like right here, give it full screen. Hit to whip. Present, yeah, hit present. Ah, amazing. What did we miss? Not much. Okay. So when we move away from the chiral limit, the medium mass is sort of where we need lattice QCD because all the scales are order 1. And the simulations that have been sort of performed over the years tell us that the guidance that we have from these chiral theories is really not very good guidance as we start making the quarks heavier than they are in nature. In particular, it predicts that the mass of the nucleon should grow like the square of the pion mass, and empirically, it just absolutely does not. It grows linear in the pion mass. And you can predict the proton mass as a function of the pion mass shockingly well with the rule 800 MeV plus m pi, as pointed out here. Okay, if you want to do better than that, you need to do lattice QCD calculations. So here is more or less everything you need to know about lattice QCD in a slide, which is that we're computing expectation values of some operator, like the current that couples to electromagnetism or a neutrino. And you can describe any sort of quantum expectation values as path integrals. That's one of the ways Feynman taught us to do it. The problem is usually just that they're infinite dimensional, and so what does that really mean? The beautiful thing about lattice QCD is you just replace your spacetime with a finite box that has some finite discretization between the points in it, so there's a finite number of points in spacetime. And in that case, your path integrals become large but finite dimensional integrals over all the configurations of that finite dimensional space. And large but finite dimensional integrals can be done on large but finite computers. And the Monte Carlo method is basically the only game in town for doing super high dimensional integrals. So what we do is we Monte Carlo sample and try and get this distribution e to the minus QCD action. And that lets us simulate any thermal equilibrium properties of QCD. And for the gluons, we really do just throw random SU3 matrices representing the gluon field and accept, reject via Metropolis. For the quarks, you have to work a little harder, and you can integrate them out analytically, which sounds great, but it leaves you with this fermion determinant, and computing the determinant of a 10 to the 9 by 10 to the 9 matrix is not something you can just do. So it has to be stochastically sampled, and algorithms for that, if you've ever heard people in AI now they like talking about HMC and for some reason are calling it Hamiltonian Monte Carlo. But HMC, also known as hybrid Monte Carlo, was an algorithm invented by lattice QCD folks in the late 80s and is the only way that we know how to sample totally non-local actions like this fermion determinant with Monte Carlo. And it's still very expensive. So this is a picture of Frontier, which up until very recently was the largest supercomputer in the world. And my collaborators and I had to get a decent chunk of time on that to have any hope of doing simulations of nuclei at physically light quark masses. The gluons, like I said, were just really throwing Monte Carlo random numbers. The compromises we have to make, I think I've already talked about, are that we have this lattice spacing that we need to extrapolate to 0. We have the size of the box we'd like to extrapolate to infinity. And the last one I alluded to but didn't really say specifically is that we made time imaginary when we wrote down e to the minus action. And we have to do that because you can't Monte Carlo sample a super oscillatory function like e to the I action. E to the I something just isn't a probability distribution. Probabilities have to be positive to sample from them. And so this trick of taking time imaginary so that you get e to the minus s is sort of an essential computational compromise that we make here. And you have to live with it. And you have to just sort of follow through what that does. So this is perhaps the one formula that is important to actually understand for this talk, which is that we don't know a priori what the wave function of a proton is supposed to look like out of quarks. We can't just plop down an ideal QCD eigenstate. If we could, we'd already have solved QCD and we'd be done. So what we do is we put down our best guess for what a proton should look like 3 quarks with some Gaussian wave packet, and then we evolve in imaginary time. And that, somewhat miraculously, acts as a low-pass filter that pulls out the ground state over all of the other states. And the way to see that is if you've had any sort of quantum mechanics class, you've probably encountered that time evolution can be represented as this operator e to the minus I Hamiltonian times the time you want to evolve. Now, if you take that operator and you group I and t together and call that an imaginary time, you've now got e to the minus h imaginary time, and congratulations, you found the time evolution operator for imaginary time, often called the transfer matrix. And if you stick in a complete set of states between any two operators separated by some imaginary times, apply that e to the minus ht on some energy eigenstates, you'll see that any correlation between two operators separated by some imaginary time can be written as a sum of exponentials, where the smallest exponent is the ground state energy of the system with these quantum numbers that you're after. So that's sort of what we do, is we put down something that looks sort of like a proton, wait an imaginary time, and then hope that we can pull off the E naught there. Okay, so you're now all lattice QCD experts, and we can move on and start applying it. And most of the work I'm going to be talking about here is done with the nuclear physics from lattice QCD collaboration, NPL QCD, which spans time zones from Assumpta Perino in Barcelona to Mark Ilya in Seattle right now. Okay, so lattice QCD is at heart a many-body method. You can stick down as many quark operators as you want, and nothing intrinsically has to get harder. You have to be more clever to come up with the algorithms, but in particular, we have recently been able to compute up to 6,000 pions in a lattice QCD simulation. The previous world record had been 70 since like 2010, until Ryan Abbott in his PhD came up with an absolutely gorgeous recursive algorithm that let us just go from 1 pion to 6,144 without having to do any additional simulations or anything that really cost serious compute time. And this is enough particles that you can really interpret what you've got as a finite density system and probe its thermodynamic properties. So we were able to compute the speed of sound of dense pion matter and see how it varies as a function of the pion density. And it shows interesting features. It goes up before coming down, and it goes up higher than the speed of sound squared over the speed of light squared of 1/3, which had been conjectured to be an unbreakable upper speed limit by ADS-CFT folks, relying on the fact that that's its answer in holographic theories. But it turns out that pion matter in QCD is able to break that speed limit for certain types of densities. And we saw that at very high energies, or very high densities, we had behavior that was different from expectations from perturbative QCD that we thought were issues with lattice artifacts in this simulation because these are super high energy states. The artifacts could be bad. But it turned out that the perturbative QCD folks just hadn't included superconducting pairing in their calculations. And when they did, it changed their approach at high densities so that it fell on top of our lattice results. We then did a second round of simulations and found that the discretization effects are actually still negligible up through these densities. And we really can interpret these as full constraints from QCD, which through bounds relating isospin and baryon number density, actually, that's the one. Allowed us to place constraints from QCD on the equation of state of nuclear matter for the first time. And what's shown here is this band where everything in gray has been excluded by either causality or our lattice simulations. And then all of these colorful curves in the middle are actual predictions from nuclear many-body theory, which, happily go right through the middle. And this has gotten a lot of buzz recently. And I'd like to really just give a shout out to Ryan here as one of the rare instances where the first authorship convention in high energy physics actually aligned with the person who did the bulk of the work. So this is all great. Why can't we just do this for real nuclei? There's a couple of reasons. The first reason people are worried about is just that there's factorially many Wick contractions. But it turns out that that's not a problem. And people have computed oxygen nuclei and silicon nuclei in lattice QCD simulations. It can be done. By that, I mean they've built the correlation functions for them. A bigger problem is that the energy gaps are really small. And they're either basically on the order of the binding energies, or given time, I'm not going to go into it, but if you have an unbound system in a box, the fact that you're in a box and have some interactions gives some energy shift proportional to the size of the box. What else can it be? And so this is a handle for how we actually learn about interactions, is by exploiting this finite volume scaling. But it also tells you that as your boxes get big, your energy gaps are going to get small. So for multi-particle systems, you inevitably have these very small energy gaps. So you need to go out to very large imaginary times to be sure that you filtered out all your excited states. And you can't do that for nuclei because of something called the signal-to-noise problem. And the physical picture of it was first understood by Peter Lepage and Nobel laureate Parisi back in the late 80s. And the idea is just that if you think about the variance of a proton correlation function, that variance is you should take seriously as some object in your QFT. And if you do that, you'll realize that the thing with the quantum numbers of nucleon times its dagger, that's the lightest thing this will plateau to, isn't actually nucleon plus nucleon bar. You can just rearrange the quark lines and get 3 pions. And 3 pions are a lot lighter than 2 nucleons. So it turns out that inevitably, your signal-to-noise ratios for anything to do with nucleons decay exponentially in this imaginary time that you're trying to filter stuff out using. And as you go to larger nuclei, your exponent just gets worse with your number of nucleons. So this is why we can't just do calculations of argon 40 directly in a lattice simulation. Okay. So for this reason, a lot of the calculations that have been done so far have been done at these heavier quark masses, corresponding to, say, a pion mass of 800 MeV. And here, the signal-to-noise problem is less severe, just because as the nucleon mass goes up, this difference between Mn and 3/2 the pion mass gets smaller. So the first generation of calculations 10 years ago suggested that nuclei get more bound as you raise the quark mass. The deuteron in this world was bound by like 20 MeV. The dineutron was also a bound state of a similar binding energy. And the evidence suggesting this was that if you do simulations with different initial states, you can evolve far enough out to where they sort of collapse on top of each other before you get lost in noise. And when you do simulations in different volumes, they all collapse on top of each other until you get lost in noise for the ground state. Then if you look at what should be some unbound excited state that should have some volume dependence, it does. And so these were the a posteriori checks that led people to believe that we had more bound nuclei as the quark masses went up. And people fit effective field theories to this to start exploring what the chart of the nucleides looked like in this world. We went on to compute matrix elements to understand the structure of nuclei in this world, saw things that were looking in qualitative agreement with what we expected. But there's still systematic uncertainties in all of these exploratory calculations of not dealing with all of these limits I told you we eventually have to deal with. And with these excited state effects of not being able to go out as far in imaginary time as you'd like. And in particular, this first generation of simulations was all done for algorithmic reasons with a setup where your initial state operator is not the same thing as your final state operator. And that turns out to mean you can get cancellations between these exponentials that could, in principle, conspire to form flat behavior before you actually reach the region of ground state saturation. And so to test this, a number of different groups went on to do variational calculations where you diagonalize symmetric matrices with lots of different choices for what the wave function of your 2-nucleon system could be, ranging from plane waves of your nucleons to a totally spatially compact 6-quark thing to exponentially localized things somewhere in the middle. And when you turn the crank, these variational calculations give totally different numbers than the first generation of calculations. And they suggest that both the deuteron and the dineutron are unbound in this world of 800 MeV pions, or at least they're not able to definitively say it's bound. Because the tricky thing about these calculations is it's like the variational principle of quantum mechanics, that the true ground state energy is always at or below what you compute with your trial wave function. We've picked a bunch of trial wave functions here, and so we know the true energy is below, say, that green point there on the left-hand plot. Or if you pick a worse basis, you know that it's below that red point there. Whereas the first generation of calculations are these 4 points down at the bottom here, which are very different estimates of the central values, but technically consistent, that they're not excluded at the level of these being variational bounds. And so different groups see consistency, like depending on what operators we put in, multiple collaborations are all saying the same thing, but the physics is qualitatively looking different depending on which cartoon of our 2-nucleon system that we're starting. So, where do we go from here? One place we can go is very heavy quarks. And if your quarks are much heavier than the confinement scale, then things start to get easier again. And eventually you approach some weakly coupled regime where you can just count your number of quarks. The mass of a baryon goes like 3/2 the mass of a pion because there's 3 quarks instead of 2. And there's a beautiful effective field theory for approaching that sort of limit, where you treat your quarks as non-relativistic, and then you look at the potentials that they interact with. So this is also a nice way to think about QED in the hydrogen atom, which is that if you look at your tree-level photon exchange between 2 electrons, this diagram looks like alpha over your momentum squared. If you look at, I think the answer is yes. And I think the algorithm for doing it is based off the Lanczos algorithm invented back in the 1950s. And this has been an exploration that I've been embarking on with Dan Hackett, a postdoc at Fermilab now. Okay, so in a nutshell, what we're really trying to do when we're computing energies is computing the eigenvalues, like energies are eigenvalues of a Hamiltonian. In a lattice simulation, we don't have a Hamiltonian because we don't have continuous time translation invariance. We only have this discrete times that you can shift by 1 lattice spacing. So the operator that evolves you in time by 1 lattice spacing goes by the name of the transfer matrix. And it's the thing that really exists in a lattice theory. It's the Noether charge of your lattice time and translations. And so the energy spectrum should properly be defined as just minus the logs of the eigenvalues of the transfer matrix. And you can think of correlation functions as just matrix elements of powers of this operator. And if you think about things that way, then the first algorithm invented in the 1920s for getting the largest eigenvalue of a matrix is to start with some initial state and then whack it repeatedly with your matrix. And every time you hit your state with your matrix, you can think about going into the eigenbasis, and everything except the largest eigenvalue is going to be suppressed. So we can write this out in lattice language if we, instead of calling the eigenvalues just like lambda, call them e to the minus energies. We see that after k iterations of applying the transfer matrix, we have something that will go like e to the minus k times e naught, plus something that will go like e to the minus k times some larger energy that's therefore exponentially suppressed. So this will eventually converge to the ground state energy plus exponentially suppressed corrections. And if you go from the bras and kets written down here into transfer matrix elements, then you'll see that the matrix elements appearing are precisely the correlation functions that I've been talking about computing in all of our lattice QCD stuff. And this log ratio of them is precisely that effective mass that I've been making plots of all talk, of this thing that converges to the ground state energy in imaginary time, but eventually gets lost in noise. So you can phrase this standard effective mass estimator as applying the power iteration algorithm to the transfer matrix. And that's just putting highfalutin fancy words on something that we already know how to do. But it suggests that you should consider applying other algorithms besides the power iteration algorithm to the transfer matrix. And if you ask an applied mathematician what's the state-of-the-art algorithms for diagonalizing some large matrix, they'll say like QR, which I don't have a good analogy for here, or Lanczos. And remembering this much and having to remind myself what exactly the Lanczos algorithm was last May when I got down this rabbit hole, the idea is a glorified version of the power iteration algorithm, where you start with some state, you hit it repeatedly with your matrix, and the new bells and whistles are that you really think about the vector space spanned by all of those states hit some number of times with your matrix. You build an approximation to your matrix of interest within that space, and then you explicitly diagonalize it. And you can prove that this gives you the globally best, in some sense, approximations to the eigenvalues of a matrix, given the information that you have available from your vectors and hitting it some number of times. So this is exactly the situation we have in lattice QCD. We have these vectors we've hit with our transfer matrix. We'd like to get the eigenvalue approximations as best we can coming out of them. The rub is that we don't have access to the vectors in our hands because they're infinite dimensional. But all we really need are the entries of the matrix that we diagonalize at the end. And you can push through the recursions in terms of the vectors into recursions for those matrix elements, which are just scalar numbers that you can compute. And so what I found is that you can compute the eigenvalues that you get from the Lanczos algorithm just in terms of a recursion at the level of these matrix elements, which are all just correlation functions. So I originally thought this rabbit hole would lead to we have to try and do lattice QCD a different way to apply Lanczos to the transfer matrix, but it turns out to be applicable entirely at the level of post-processing our correlation functions that we already compute, and gives you a way to feed in those correlation functions and get an estimator for the ground state energy that converges faster than the usual one, as well as a tower of estimators for increasingly many excited states. You can prove that the convergence is faster, and remarkably, our applied math friends have shown that you can compute a two-sided bound on your approximation error after a finite number of steps. If you've worked with anything like the conjugate gradient algorithm, it's a very similar spirit where you just compute the residual norm of the difference between your approximation after k vectors and after k plus 1, and you can get some rigorous bound on your approximation error from true in a two-sided sense on this. Okay, caveat, you don't know that you found the ground state. You could always add plus 0 times e to the minus a smaller energy and you never see it, but you get a two-sided bound that you have identified some eigenstate and found some true energy in the QCD spectrum. Where conservation of evil shows up is that, like I said, you don't just get one eigenvalue estimate, you get many of them. With exact data, they all converge beautifully to exact things in the spectrum. With noisy data, most of them just don't converge at all, and you get just increasingly many pieces of spurious garbage out from the algorithm as you go to later and later times. Fortunately, there's been like 70 years of applied math research on the Lanczos algorithm. And it is well understood, to those who understand it well, that spurious eigenvalues also show up in the presence of finite precision roundoff. They show up specifically because of loss of orthogonality between two of your would-be orthogonal eigenvectors, and their existence doesn't spoil the convergence of all of the non-spurious eigenvalues. So you get a mix of eigenvalues that converge and background garbage that doesn't. State-of-the-art methods involve doing some selective reorthogonalization to just prevent these spurious things from appearing that I have no way to apply in this recursive setup. But we've learned how to think about noise from a few more applied math friends. And you can think about splitting your space up into physical eigenmodes that you believe and unphysical ones that you don't. And you just need a criterion for unphysical. Complex eigenvalues is a good start. We'd like our energies to be real. It turns out the other criterion you really need to impose is that the states that you're finding have some non-zero overlap with your initial state. That's what we believe we should be doing. We should be starting with some state and then finding all of the true states that have some overlap with it. And so if something's coming out of your algorithm that has approximately zero overlap with any of the states you started with, it's probably noisy garbage, not actually a signal of a physical state. That intuition can be made precise according to a beautiful piece of applied mathematics I cannot hope to summarize in a few sentences by Jane Cullum and Ralph Willoughby in the 80s, who invented something called the Cullum-Willoughby test for post facto removing these spurious eigenvalues. So I adapted that Cullum-Willoughby test, and then Dan and I figured out that it was actually formally equivalent to just this physical picture of cut out the things with low overlaps. And so our ZCW test, or the original one, takes you from this forest down to this set of seemingly plausibly converged eigenvalues that don't predict any things that you know are wrong, like the nucleon should be lighter than a pion. We can throw it at problems where we already know the answer, and it works. So this is a glorified simple harmonic oscillator that we compute with a noisy lattice simulation, and we get convergence to the right answer. And after you've filtered out all of these spurious eigenvalues, then these Lanczos energies don't share the annoying feature of the power iteration effective mass of having these exponentially growing error bars. The error bars approach a constant at large time in much the same way as like the errors from performing a fit as you extend the end of the fit range, because the Lanczos algorithm is really using all the information in the correlator up to the maximum t shown, and is able to then, after applying this filtering, remove the components that give this exponentially growing noise. So you can get answers really easily without having to do all of the horrible data analysis of fitting things with exponentially growing noise, and get these two-sided error bands out on how far off you could be from true. And this is the hammer that we have been looking for how to try and understand this two-nucleon controversy at intermediate quark masses. It turns out that you get one more useful perspective on that problem from this Lanczos point of view, which is that if you have an asymmetric correlator, the matrix elements you're calculating are really, you should interpret these as some off-diagonal matrix element of your transfer matrix. And it's, again, provable linear algebra that you get the best possible approximations to the eigenvalues of some operator from precisely not those, from the diagonal matrix elements of either of the two states. So it could be the case that the asymmetric correlators had found the true physical ground state, in which case either the initial state approximation of it or the final state approximation of it should have gotten to the true ground state, and now when we compute the symmetric matrix element of that state, it will give us a lower energy than came out from the second generation variational calculations, but with enough guarantees to prove that there is really a bound state there. But that's not what happens. What happens is that these diagonal matrix elements are not at all at the same place as the off-diagonal ones. And this plot should say both preliminary and blinded, so don't read the numbers at face value. But even before unblinding, we can tell that these symmetric versions moved away from where the old asymmetric correlators suggested there could be a ground state to something that is right on top of the variational calculations. So, properly interpreted, the old asymmetric correlator data does not provide any rigorous evidence in favor of the existence of bound states. And all of the rigorous evidence that we can get out from any of these is consistent only with the hypothesis of unbound. That doesn't mean we can't, it's very hard to prove that a bound state doesn't exist, but what we've been able to say is that all of the simulation data that we've analyzed to date, when interpreted properly, does not give any evidence suggestive of a bound state. So, why do nuclei stick together? The quarks are light. We see that for asymptotically heavy quarks, there do not exist the gluonic van der Waals forces that you would need to have a picture of the deuteron as a gluonic molecule. You only see that sort of thing emerge at very high orders where you also have spin-dependent interactions that suggest a complex web of what baryons might bind rather than anything universal coming from gluon exchange. On the other hand, in lattice QCD, then we see that we have no rigorous evidence for bound deuterons at intermediate quark masses. We do have some rigorous evidence for bound states made of two hyperons. So we know that at least some bound states do form in this intermediate quark mass world. We don't have the full catalog yet understood of what flavors and what interactions give rise to what kinds of binding, but I think that we have now understood enough to be able to say that nuclei in QCD are either strange, finely tuned, or both. And with that, I will leave you and take questions. Yeah, that's right. You shouldn't think of like a 300 MeV constituent quark is not really the right picture in that if you like compute you can break up the stress energy tensor into like a part coming from quarks and a part coming from gluons. And when people have computed those matrix elements in lattice QCD, the gluon part is just dominant by more than an order of magnitude. So it really is like, unless you want to call your constituent quark mass like that cloud of gluons, which is kind of cheating, like the mass comes from the gluons. Different language. Yes. Yes, and we would love to be able to make predictions for lambda hypernuclei. That's on the list. Once we settle 2 nucleons and move on to 3, get down to physical quark masses, there's still lots to be done, but we're getting there, and I think we've got the artillery to be moving again.
But if you look at argon-40 or something, where are your antinucleons? So why is this an issue?
Good. So our signal is like 3 quark propagators. And the thing that I glossed over here is that your quark propagators have a complex phase. They're charged under baryon number, so they kind of have to, and you can think of it physically as like the Aronov-Bohm phase of your quarks moving through this gluon plasma. But in any case, your Monte Carlo samples are complex numbers, sample by sample. So what is the variance of a complex number? Hard to define. The best thing you can say is what's the variance of the real part? And so then if you're trying to say the variance of the real part of a nucleon correlator, this is the variance of the real part is just 1/2 C plus C star. And so this is really the trick, that you get this CC star contribution plus other stuff. And that's your nucleon and antinucleon. Yep. Yeah, good question. The day, I'm happy to chat with anyone.